just start. And so this is, I would say, still quite an early work. I recently joined well, not recently joined the Newcastle University, but I switched supervisors, and now I'm working with Sergey Bogomolov at Newcastle University. And we started this kind of new work with our colleagues from NZECT from Toulouse, where we're trying to kind of look at the synergies or between proof-based and reachability-based system verification, and maybe more generally hybrid cyber-physical system verification. And because of Sergey's background in reachability and his kind of PhD students who work with JuliaReach, we decided to kind of investigate this field a bit more. And so I think I'll need to give a bit of a background on this method called EventB, which we use as kind of our main modeling language. And then I'll try to explain with example how we're trying to kind of connect and what kind of benefits JuliaReach and reachability analysis can provide for us, specifically in system verification. And I'll just kind of finish with some potential next steps which we like to do. Okay. So I'm not sure how many of you heard or know there's a formal modeling method called EventB, or even the predecessor called B method. It was developed by a French computer science named Jean-Ramon Abrial, quite a long time now. And there was the original method, B method, was developed for software verification. Years later, he introduced an evolution of that method called EventB. And unlike just being purely for software verification, method kind of aimed at modeling systems, much larger systems. So just compared to the software systems. I think kind of just to maybe say this, that the methods are not just kind of used in academia, but they have been used quite widely in industry, and quite specifically railway industry by companies like Siemens and Alstom and others who have been using to develop safety critical software and other railway related systems. And more maybe on scientific note, the modeling notation is kind of based on set theory. And one of the key aspects of this EventB modeling language is refinement or stepwise based development, where you kind of start with the abstract view of the system, and then through refinement steps, you add more detail. And what, in addition to refinement and modeling, you complete proofs. And the main platform for modeling EventB models is this Rodin platform. But over the years, quite a few new plugins to this Rodin platform have been developed to improve verification, or to allow extending kind of static mathematical language, which was EventB based on through this theory plugin. So maybe just to kind of give a small example of what EventB model looks, and then I'll move to hybrid EventB and how this all relates. But just EventB model has this kind of context where you put like static information about the model, such as axioms, constants, other sets. And then you also have a machine, which kind of describes what this the dynamic part of the system, where say the states are updated, or what basically a system is doing. And here I just have very, very basic kind of addition example just to show you what kind of looks like, where you have, for example, just one variable in this one machine, X, and it's just a natural number. And what you have in EventB models are events, or basically for any EventB model, you have initialization event, which kind of sets the initial value. And then you can introduce new events which update the state variable, in this case, X. And for the events, you have the guard, basically as some sort of predicate, which tells whether this event is enabled, and then just an action. So for example, in this case, we just really have some sort of X value, which is initially 0, and you add 1 until that X is less or equal than 10. And one of the key kind of things what you try to do in this modeling you try to add properties about the system called invariants. So for example, we want to add and prove that the X never goes above 11. And what this kind of tool and the approach does, it generates you so-called proof obligations. So kind of like like some sort of things you want to prove in the first order logic, and you need to discharge them. And for example, if we have invariant about X, in this case, we would be generated two kind of proof obligations we would need to prove. And there are other kind of proof obligations. In total, I think there are 10 different proof obligations about the consistency of the model. So for example, whether your variables are well defined, you can have, I'll talk a bit about feasibility and other things. But this is kind of purely for discrete models, which was originally developed, and the verification automation has been improved quite well, where, well, I would say most of the discrete models now can be automatically proved. And there has been developed a model checker as well. And now I'd just like to focus on two types of proof obligations, which kind of relate to this continuous or hybrid work in JuliaReach. So first, as I already mentioned, there is this invariant preservation rule, where, for example, you want to add some sort of property to proof, and then the tool and approach, like I said, generates two proof obligations. So for example, here there is one where, for example, for this increment event, you need to prove that this invariant holds. And we also need to prove like the base condition, where that we need to basically prove that initial event also satisfies invariant too. And it's just like so-called proof by induction, where you prove the base, and then you prove every event which modifies X. And another kind of proof obligation, which is really related to our approach for modeling hybrid systems, arises from using a slightly different assignment. So for example, here we just really have direct assignment, but in event B, you can even write things like that, where you, for example, say that the next value of X is such that it'll be basically +1, and plus you have another predicate. So for example, if we consider this case, and we can almost automatically prove that this holds, because we already saying that we want to update X such that basically invariant preservation holds. But what happens in event B, you are generated a new type of proof obligation called feasibility. And basically what feasibility asks to prove is that such X prime, the next value of X, actually exists. So basically, just to kind of quickly summarize, we are particularly interested in two types of proof obligations about kind of invariant preservation, and what in showing that these feasibilities kind of exist. And kind of even I'm saying here that you can kind of even strengthen the predicate of this assignment such that invariant is almost like automatically proved, as long as you can prove that there is a feasibility of such event. So just to move like towards hybrid systems, what happened in the last, I think maybe 10 years, a new plugin has been developed, which a theory plugin, which allows to extend event B mathematical language. And people like Richard Barnach or my colleague Guillaume Dupont use that kind of tool to extend event B mathematical language so that hybrid systems could be modeled. So for example, what Guillaume and his work in his PhD thesis did, he developed new event B theories for modeling or capturing real numbers, continuous functions, differential equations, and theory of approximations, which were not previously present. And he also developed hybrid system modeling patterns and refinement patterns. So we developed event B events such as like that, where you can kind of capture a kind of generic hybrid system where you have actuation events, you have sensing events, you have transition events, and you have behave events. And the idea of his was that his patterns provide this generic hybrid system modeling, and by using event B's refinement pattern, you can then develop some sort of specific hybrid system of what you want and prove properties. But his patterns provides this foundation for how to model systems. And just to how kind of it looks in EVMB, he now in this with his modeling patterns, with Guillaume Dupont's patterns, you still have some sort of discrete states and discrete variable, some sort of XS, but you also have a continuous variable XP, for example, some sort of plant variable, which is a function from reals to some state. And I'm just showing you here two types of generic events, and there are 4 in total, but just to capture for discrete generic model, you still have some sort of sense event, for example, representing a scenario where a system senses something happened or change in the plant, for example, captured by the guard, and it say jumps to the different mode. But kind of what we really interested in this work, which I'm going to continue about JuliaReach, is about events which change the plant or model the plant. And for example, here we have actuation event, where we update a plant variable such that for some sort of time period, some sort of predicate holds and is within this evolution domain of continuous function. So this level is still quite abstract, and the idea is that you would kind of refine this event to say model the acceleration or falling or some sort of actuation event. Maybe not to go too deep into these guards, but guards basically ensure that, for example, that time duration you look and t prime is greater than the current time, that the solution for this kind of part actually is feasible, and this kind of would actually help to do some proofs. But like I said, maybe just to show here that instead of direct assignment for the update of the plant variable, we use that notation such that, so we just update continuous function symbolically, saying that updated such that this predicate is satisfied and that function remains within some evolution domain. And from this, we get 2 kind of new types of proof obligations about the continuous function or continuous kind of aspects of the system. We get the continuous invariant. We basically ask to prove that evolution of this XP variable is within this domain, the safe domain, for example. But we also want to, in some cases, we need to prove, and for each actuation event, we need to prove that such evaluation actually exists and can stay within some sort of bounds. However, the biggest crux of this whole work, and actually maybe more general deductive hybrid system verification, is really just proofs being manual and you needing to do interactive proofs. And they are quite complex, and typically you kind of result in really big pen and paper proofs at this stage. So there is this kind of trade-off where perhaps this language is a bit more expressive and you can model like more different systems, but when it comes to verification, a lot of properties on the hybrid, on the continuous aspects are still hard to prove automatically. So, and key kind of idea and what we're trying to explore is how we can kind of combine JuliaReach and maybe more general reachability analysis with event B and this kind of proof-based system development. So as I said, like a long term is really to use event B as a kind of essential or core modeling languages, modeling languages for modeling systems, especially cyber physical systems, and then kind of see how we can connect to reachability analysis. And now we kind of moving towards just really connecting to JuliaReach. And through discussions, we identified at least some potential directions. So in the next couple of slides, I'll focus on the main one where we want to try to automate some proofs by kind of exporting some verification obligations to JuliaReach. But we also discussed that in some other directions could be really just proving, for example, submodels of event B models. For example, you have large cyber physical system where event B model captures the whole of it. Using refinement and this kind of decompositional approach, we can, for example, prove parts of the model in JuliaReach, return the proved kind of statements and prove other properties in event B, for example, related to more to discrete parts or communication aspects of the system, etc. Another maybe two kind of interesting directions and what we like to do is to explore how JuliaReach and reachability analysis could be used in discovering constraints and safe parameters. This kind of specifically, I guess, relates from one reason to, for example, when you have in this example here, discovering what guards we need to use. And this becomes a bit more complex when we have hybrid systems. We also kind of want to see how we can use JuliaReach and to go towards code generation where we have this purely continuous model. And then by using reachability analysis, we want to find that delta t for which it would be kind of constrained. And kind of initially we looked at different tools, but we now solidly set on JuliaReach, and I kind of was leading that part. And I think I was kind of impressed by just that is basically quite a modern tool based on this new powerful language. One of the key kind of things I looked was this arch competition, and I saw that JuliaReach performed quite well, especially in the parts for nonlinear hybrid system verification. And especially for us, maybe because of our kind of still explorative work, it's an expressive kind of tool set as well, where we can try to do quite a few different things. So in the next couple of slides, I'm just going to present an example of how we try to combine JuliaReach and event B. And I'm going to present an example from railway. So where we try to model a cyber-physical railway signaling system. And we know, probably most of you have been on trains, we know that trains or rolling stock are hybrid systems. They accelerate, decelerate, so we have these physical properties. Nowadays, they're mostly like driven by computer-based systems. But we also have other safety critical and kind of key components such as communications center and interlocking, where a lot of decisions for trains are being made, and for example, what safe separation is being issued from these kind of components to the trains. So for example, trains can change how quickly, how fast they want to go and when to brake, but these other components from railway signaling system provide that information for how long you can travel, for example, and then train needs to decide at what speed. And that seemed like a good example because a lot of parts about the rolling stock and physical properties can be proved kind of more like on the JuliaReach side, whereas all that communication and how that safe distance is computed can be proved on event B. And just to show, we considered a train hybrid automata, and we wanted to have a bit more complex train model where we used nonlinear equation, and this is how commonly is used by railway engineers, where they use a so-called Davis equation, where it has like three parameters which are based on track resistance or drag and other coefficients. So these A, B, and C are some sort of coefficients, and we used specific ones from the French standards. So we have one, I think I might have made a mistake, is missing a minus, but we have one mode where a train can accelerate, we call it free mode, and we have another mode where it decelerates basically. And that really depends on two things, in which mode it is. We have this end of authority a value, which basically says, for how long a train can travel. And if we know that our position is still before that end of movement authority, we can still accelerate. And we have that stop distance function, which takes acceleration and current speed and produces that stopping distance. So we just need to check whether the current position plus the stopping distance needed is greater or equal than the point we want to be in, or allowed to be. And just kind of how it looks on the event beat. So here, maybe I didn't mention, we have this traction effort. So if a train wants to accelerate, you kind of make induce force through this traction effort. And we have this end of movement authority, which we just model as some sort of function from time to some value. And we have some speed for safety as well. But I just kind of want to focus on specific event. So for example, if you have actuation move event, where we try to model a free mode where a train accelerates, we have kind of events like that where we have two guards that basically want that TA and TV to be, such that the train would stop before some authority, and we would update in the action our state variables TA, which is acceleration, speed, and position, such that basically we stop before that point. So, and what happens is this is almost impossible to automatically prove in event B, and this is what we had some problems with, and we decided whether maybe we could connect this not only event but more like a proof obligation we want to prove in JuliaReach. So instead of proving directly in event B, we basically translate this, and what we want to try to prove, we strengthen firstly this kind of predicate, and we want to show the feasibility of such event. So we want to at least show that there is an instance where this basically holds. And I just kind of try to write down the steps of what we do. Is basically we first strengthen the evolution domain of this action such that the global invariant property holds. And from there, we can almost automatically discharge the say invariant that say train stops all the time before this end of movement authority. But then what we get feasibility proof obligations we need to prove. And since we had the two modes which both updated the plant variables, we get two feasibility proof obligations we need to prove. So, and what we need to basically prove that there exists input to that system such that basically it can stop. And what we currently try to do is we manually translate each mode separately to JuliaReach, where, for example, for free mode, we just create a function, Taylor as function free. In this specific instance, we also needed to translate at the moment manually some other functions which will be used in the reachability analysis. So for example, stop distance function. And what we do, we basically compute some sort of reach set for some time, and we need to provide, of course, all initial values and time. And we really just want to check from the solution provided by JuliaReach if such an interval exists for which the safe bounds are satisfied. And if it does, basically we have at least a feasible solution for this specific system. So we can kind of prove the big invariant by proving at least that there is a feasible solution for this part. And just maybe one kind of snapshot from what JuliaReach produces. Of course, we don't kind of need this, but this is just kind of plot from the one of the modes in free mode, where we just kind of plot the position, reach set, and speed, where basically just train accelerates. And because of this kind of nonlinear Davis equation, speed at some point just kind of reaches the steady state. And maybe at very core, what it helps to do is to improve verification automation. So for example, previously we had here 19, I think it will be 19 interactive proofs based on the speed controller on this hybrid model. But we were able to shrink down by 7 proof obligations because we kind of use the reachability analysis in JuliaReach. And so far, we can only really kind of focus on this invariant preservation and feasibility. But I think in the future, we'd like to kind of address all the other aspects. And maybe just kind of on a more general case where with this kind of modeling approach, we can also prove other properties about a system which are not that much related to the hybrid aspects or continuous aspects. And these are quite automatic. And we had another refinement of the railing train model where we model communication and how that safe distance is basically computed for the train. And just maybe just to finalize what we plan to do in the future, I think it will be the most important task to provide a automatic translation from event B to JuliaReach. We feel they're still kind of missing some theories on event B. And one thing I kind of really missed was, I think, being able to describe systems in the matrix form in event B, because quite a lot of examples from JuliaReach, or could maybe even some works much better, or only works with the kind of this matrix format. And I think kind of just more generally, we really want to continue exploring synergies between proof and reachability analysis and kind of this JuliaReach area. So I think that's about it. I have a couple of references, and I would like to share slides if you'll need it. So thank you.
Yes, thank you very much for the very interesting talk. Let's give our speaker again a virtual round of applause. So if there are questions, please feel free to ask.
Maybe just a comment. So first, it's cool that you can use JuliaReach for your work. Interesting application. I just, when I saw this work, it reminded me of another approach to hybrid system verification, which is not by reachability analysis, but by some, well, I don't know, some, I would say, more theoretical works. It's implemented in the tool Chimera-X.
Mm-hmm.
I don't know if you do know about this. And that might be very well suited for the types of problems you have, where you have some proof obligations. So it's really about proving hybrid, they call that hybrid programs.
Yeah, we are aware of Andreas Platz's work. I think our kind of maybe, and we discussed what are advantages, because works are very much related. I think event B, in compared to what is called hybrid programs, allows to refine, has this kind of refinement feature, which is nice when you deal with a bit more complex problems.
Mm-hmm.
And I think, and well, he doesn't use reachability analysis, he uses Mathematica. I think it's called Mathematica. It's gonna.
Yeah, I also don't know the details, but it's, I think it doesn't use reachability analysis, but really just reasoning about, I don't know, some more complex, I would say, theories.
Yeah, and I mean, he has quite a large group, and he has quite a lot of work in this area, and we very much relate. I think we kind of discussed that reachability analysis can potentially provide a bit more, especially in the kind of providing some constraints, whereas what he has is it's more like, it's a slightly different approach where it provides the differential equation. It gets kind of symbolic representation of that.
Yeah.
But
okay.
Yeah.
Cool.
No, thank you very much. Okay.
Yes, thank you. I think maybe we have time for one last quick question, if there's such.
So, could you explain a bit the table that you have towards the end of the presentation? Yeah, what does this represent? Can you comment again, please?
Oh yeah, I think we want to quickly. So I hope I mentioned that was clear that when you model something in event B, you generated these mathematical proof obligations you need to prove. So for example, you have here well-definedness. So for example, you use, let me just think of a very quick example. Say you use some sort of function in event B, and you need to prove property that this is actually a function. There are some other kind of properties about guards, and I hope I mentioned these are like invariant preservation, and this one is feasibility. So this basically generates proof obligations when you include invariants. So for example,
Okay.
like here, you want some add property, and you are generated a property in proof obligation you need to prove. And some of the properties or these proof obligations can be proved automatically. So there are enough tools where you just press the button and basically gives you, whether that kind of holds or, proof.
So
And
is it
sometimes-
related to the discoverability concept that you mentioned before?
For example, feasibility, yes. So for example, feasibility proof obligation asks whether there exists some sort of, for example, I think sometimes it's a bit easier to present if discrete. But for example, here asks, does there exist x prime such that if you add 1 to x, well, basically it'll be less than 11.
Mhm.
And you need to prove that such x prime exists. So for example, in terms of hybrid systems, you will have, does their input to system exist such that it stays within, say, some bounds? So for example, you have a water tank model and says like, if I put that much water, is there exists such input to the water tank, but say it stays between some 2 levels or something like that. And you need to kind of prove that it does. And generally, these are very complex proofs to do. So, and that's why kind of it seems a bit more natural to use reachability analysis or some sort of mathematical solvers where you can do that. Of course, kind of the problem is that reachability is bounded, whereas most of the model or the idea of FMB is like to prove for unbounded, models. So we can have this trade-off where we basically show that instance of this model is safe. If it makes sense.
Yeah,
Yes.
thanks.